Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to finish up a three-part series looking at some successful strategies for working with the free response questions on the AP Calculus exam. If you missed parts 1 and 2, later in the webinar we'll discuss how you can go back and look at those for free, but it shouldn't affect your learning tonight. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm excited to be joined by our two panelists, Vickie Carter and Steve Kokoska. Vickie's been teaching high school math for 44 years at West Florence High School. She's a former co-chair of the AP Calculus Development Committee and served as an exam leader at the AP Calculus reading in the summer of 2018 and 19. She received the T-Cube Leadership Award in 2015 and has served on TI-Nspire authoring teams and has presented at many national, state, and local conferences. Vickie, it's great to have you with us tonight.
It's a pleasure to be with everyone here tonight.
And Steve is a professor in the Department of Mathematical and Digital Sciences Department at Bloomsburg University. He is a former chief reader of the AP Calculus reading and a member of the Development Committee. Steve is an active T-Cube instructor and College Board consultant with recent workshops in China and Singapore. He just published an AP Calculus text and the third edition of his Introductory Statistics text. Steve, thanks for joining us tonight.
Thank you very much, Michael. It's wonderful to be working with the two of you again.
We're expecting a large crowd, so your audio is muted. Feel free to send any messages to Vickie or Steve using the Q&A window on the right side of your screen. We'll also be in the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Steve is going to discuss our agenda.
Thank you very much, Michael. Well, we've already done the welcome and introductions. After we're done a little bit more with this introductory stuff, I'm going to talk about question AB6 on the 2019 AP Calculus exam. I'll review the question quickly, and then I'm going to spend a lot of time on the scoring guidelines. I'll talk about some common student errors, and we'll see exactly how some responses were scored. And I'm even going to throw in a couple of polling questions this time. We're going to try for a little bit more interaction. So we have at least 4 polling questions to keep you on your toes this evening. And then I'll pass the screen over to Vickie, and she'll talk a little bit about technology strategies. And at the very end, it'll come back to me, and I will leave you with one problem extension that is part of the TI in Focus AP Calculus video series. And then I believe there's a webinar drawing. I think it's for a BMW 540i this week, isn't it, Michael?
I think equivalent to that. I don't know if it's the BMW version or it's the T-Cube Summer Workshop. They're worth about the same, I think. But,
I see. Thank you.
Yeah. Yeah, so stick around, everyone. We'll be giving away to one lucky winner a T-Cubed Summer Workshop drawing at the end of the webinar. And Vickie is going to discuss our expected outcomes.
Well, we certainly hope that you'll have a better understanding of how the 2019 AB6 question was scored this past June in Kansas City. We are going to talk about some technology, even though this was not a calculator active question. There's still some rich calculator things that you can do with your students to help them understand the concepts that are within this question. And then, as Steve just mentioned, we're going to look at some problem extensions that might help a little bit with AB6. Now, we all know there's a lot going on in the U.S. right now, and probably on everybody's mind is what is going to happen with the AP exam. Well, we don't know, but I wanted to mention and show you actually where you can locate this information. If you go to AP Central, for those of you who are AP Calculus teachers, and I am one of those, we have an alert here, and if you click on this hyperlink that says Learn How We're Supporting Schools, we'll see what we have to say here. So right under the last notification was March 16th, and it says, as you can read, that the AP program is developing some resources to help students, and the important thing that I want to point out is that additional information will be posted by March 20th. So tune in Friday, and maybe there'll be some information that can help you with this situation that we have with lots of schools being closed. All right, so now I am going to send this over to Steve so he can start with his presentation of the 2019 AB6.
All righty. And did you send it here?
Well, I
yes.
did.
And Vickie, before I begin, may I ask, did I see a note also from Texas Instruments that they're working on a plan to do some extra support for teachers during these trying times?
Yes, and I think I saw something similar. Mike?
Okay. Yeah, Mike, do you know anything about that?
I know I also saw, I think I saw an email come through. I'll double check on what that is.
Okay.
Thanks so much.
Okay, well, thank you very much for joining us this evening. Again, these are very trying times, but let's see if we can have a little fun with AP Calculus here. If you're seeing my screen on the left-hand side, you'll see a statement of the free response question AB6, and I'll keep that up on the screen. On the right-hand side, I have a set of slides that I'll be going through, and I'll also be bringing up a couple of polling questions if everything's working correctly. So this is AB6. This is the last problem on a long exam for the students. And I have to tell you, I'm going to get too excited about this problem because I thought this was just really cool. Reading this problem reminds me of a problem written several years ago by one of Vickie and my friends that dealt with almost every single kind of approximation that there is in AP Calculus. That was one of the coolest problems ever. And this one was actually pretty cool too. It involves all kinds of functions, lots of letters, L'Hopital's rule, and son of a gun, even the squeeze theorem. So let's take a look at this. I've toyed with drawing rectangles on the screen here, but I just think it gets too busy. If you can follow my hand there, I'll try to use that a little bit on the screen. So first of all, in this problem, we're given some functions f, g, and h. And we're told that they're twice differentiable, and we know the values of g and h at 2. We know that h of 2 and g of 2 is equal to 4. We're also given a tangent line to the graph of g and the graph of h at x equal 2. It's the same tangent line. In part A, all we need to do is to find h prime of 2. I say that with a little bit of simplicity. All we need to do is to find h prime of 2. And in part B, a new function a is defined, and we need to find both a prime of x and a prime of 2. And just as an aside, this is just my own observation. I think this is one of the few times that we'll actually see, that we have seen, a question that asks for both the general derivative and then the derivative at a value 2. Usually this just says find a prime of 2, and we expect the student to find a prime of x first, but unfortunately many don't. But by asking specifically for a prime of x, this is just my own observation. I think it makes it a little bit easier to grade, and it also sort of directs the student, gives them a little bit of an implicit hint as to what to do first. I think that's a good thing. In part C, we have another new function defined, Holy Toledo h, and we know that the limit as h goes to 2 of h of x can be evaluated using L'Hopital's rule. So this is a little twist here. And we need to use that fact in order to find two values, f of 2 and f prime of 2. And then in part D, we're given an inequality involving g and h, and another inequality involving a new function k, another new function. And we need to determine whether k is continuous at x equals 2. Wow. There ought to be about 27 points here. Well, part A was worth 1 point. And it was worth 1 point simply for the answer 2/3. Part B was worth 3 points. The first point was for the general form of the product rule, and we'll talk more about what that general form looks like. This general form of the product rule necessary in order to find a prime of x. The second point was for, well, the correct expression for a prime of x. And the third point was for the value a prime of 2. Seems pretty straightforward. Part C was worth 4 points, and boy, there's an awful lot of writing here on the scoring guidelines. Let's see if we can decipher some of this. The first point over here was for recognizing or connecting this limit to that value h of 2, which was 4. And the reason that that's true, although the student, you'll see, doesn't have to state this, but the reason that that's true is because h is continuous. The second point was for finding the value of f of 2. The third point was for appropriately conveying the use of L'Hopital's rule, and we'll decipher a lot of this more in a couple minutes. And the fourth point was for actually finding the value of f prime of 2. And part D was worth 1 point, and boy, there's an awful lot of little things necessary here to earn this 1 point. But generally, we need to see that the student concludes that yes, K is continuous, and they have to provide sufficient justification for this conclusion. And we'll again go through a lot of this in a couple minutes. Now, before I actually get to dissecting the scoring guidelines, I want to give you a couple of general comments about student performance on this question. So I still have access to all of the question leader reports, and so I've tried to summarize this and give you a little bit more background here about what students did right and what they did wrong. So in part A, most students recognize that h prime of 2 is the slope of the tangent line to the graph of y equal h of x at x equal 2. That's a good thing. And therefore, most students did report that h prime of 2 is 2/3. However, the most common student error here was that h prime of 2 is equal to 4, the y-intercept of the tangent line. I'm not sure why, except maybe that 4 was screaming out at them. Not sure. In part B, most students knew that in order to find a prime of x, they had to use the product rule. That's a good thing. However, unfortunately, I think that there were a lot of non-calculus errors here. Some copy errors, some parentheses errors, and some incorrect derivatives of a simple function here, 3x cubed. Now, most students knew that they needed to evaluate a prime of 2 once they had a prime of x, but there were several simplification errors, again, non-calculus errors. So I think this is a good point to remind you that final numerical answers on the AP Calculus exam don't need to be simplified. Now, it might be different in your class. It's certainly different in my class. But under the pressure of a high-stakes exam, you don't need to simplify final numerical answers. In part C, few students indicated that h is continuous at x equal 2. Many students simply didn't connect that limit as x goes to 2 of h of x to h of 2 equal to 4. Just didn't see it, didn't make that connection. Now look, most students understood they needed to use L'Hopital's rule here, but there were some errors in the derivative, generally in the denominator of that expression. Many students were able to find the correct value of f of 2, so they got sort of halfway through this problem. But fewer students were able to find the value of f prime of 2. Now, the most common error here in this problem was with notation. And the way that I've written this on the page here, the limit as x goes to 0 of h of x equal to 0 over 0, was interpreted as an error in notation. Now, I'm going to talk more about that in a minute or two. Some of us disagree with that, and we'll talk more about that in a minute. Down here in part D, few students presented a complete justification to earn the single point. As I said, there was an awful lot going on here to earn that 1 point. The most common errors included failure to mention that G and H are continuous, no discussion of the limit as x goes to 2 of k of x, and unfortunately there was some use of some incorrect theorems here. For example, several students tried to use the mean value theorem or even the intermediate value theorem here. All right, so let's go back to the scoring guidelines. Let's see how we can score some student responses, see what students gave us, and interpret these scoring guidelines in a little bit more detail here. So again, part A was worth 1 point simply for the answer. And this had to be our answer, and it always sounds funny when I say it and when I write it, but it does have to be our answer 2/3 here. And the reason that I say that is sometimes when a student makes a copy error or they add an additional minus sign or they lose one, we're often willing to read with them for their answer, but not in this case. This question or this part was worth only 1 point. It had to be our answer. So in this part of the problem, the 2/3 could be presented unsupported or even unlabeled, and the student would still earn the point. If the 2/3 was included as part of the tangent line equation, then the 2/3 had to be boxed or circled or highlighted in some way. So a presentation of the tangent line equation didn't get them or earn them the point.
Steve, let me interrupt there just a second.
Please.
It's something that students tend to do a lot. It's when we ask them for the slope of a tangent line, they proceed to write an equation of the tangent line. Please tell your students to be very careful about which we ask for and what they should put on their paper.
Good point. If the student wrote y prime is equal to 2/3, in this case, that was okay, and they earned the point. And again, to kind of connect this with something I said a little bit earlier, the most common error here was to identify the y-intercept as part of the tangent line equation as the derivative. So many students wrote h prime of 2 is equal to 4, and of course that didn't earn the point. All right, so part B was worth 3 points here, and the students had to find both, remember, both a prime of x and a prime of 2. So let's see, the first point was sort of the way that I think of this as a conceptual point for demonstrating the general idea, the general correct form of the product rule. So what does that mean? The expression presented does not need to be labeled as a prime of x, but the general form has to look like this right here, where p of x and q of x are polynomials. So this form of the product rule means the following. It has to be the sum of two terms. H of x has to be one of the terms. H prime of x has to be the other term. And both h of x and h prime of x must be multiplied by polynomials. So you can't introduce a log function or a trig function. So the second point in part B was for the correct expression. So first we look for the correct form, and then we see, do they have the correct expression? And again, this doesn't have to be labeled. And here's a correct alternative form for a prime of x. Many students gave us this kind of factored form, and that was okay. And here are some examples of student responses and how each was scored. So let's try to apply this information that I've given you. In example 1 here, there is no sum of two terms. So the response doesn't earn the first point, the form isn't correct, and they're certainly not eligible for the second or the third point. So that's what this means over here is 0, 0, 0. In example 2, the form of the product rule is correct, but I think this 3x squared term is incorrect. So they have the form correct, but they don't have the correct expression, so that's a 1, 0. But there's a question mark here, so we're going to be willing to read with them for the third point. In example 3, the form is incorrect. You see that they have the sum of 3 terms here. So this doesn't earn the first or the second point, and this student isn't eligible for the third point. Excuse me. And in example 4, the form is correct, but one of the terms is incorrect. Multiply through, one of the terms is incorrect, but this is eligible for the third point. So this is a 1, 0 question mark. Cool. And let's see, the third point, excuse me, the third point in part B was for the value A prime of 2. And as in many questions here, there is an eligibility criteria in this part of the problem. The student must have earned the first point, form of the product rule point. Now, there was an exception here, and if the student used the tangent line expression h of x. Now, I'm not going to go through this with you, but I want to assure you that we did have a fair way of scoring this solution at the reading last year. So let's see, if a prime of x was incorrect, but of the correct form, then we would read for a consistent answer. That might take a little bit of time, but we felt that was the fair thing to do. If h prime of 2 was incorrect from part A, then we would still read for a correct answer. If the student wrote a prime of x equals a prime of 2, that was interpreted as a linkage error, connecting two things with an equal sign that really aren't equal. Or bluntly, it's just bad notation, and the student did not earn this point. And unfortunately, there were many unsimplified forms, that were certainly okay. So down towards the bottom here, again, here are a couple of student responses. Let's see if we can put this all together and how they were scored. In example 1, the student has the correct product rule form, got it, but they've made an error. Let's see if I can find it. I think the 6x squared is incorrect. So they're eligible for the third point, and I believe they found a prime of 2 correctly. So this is scored as a 101. In example 2, let's see, they've got a correct form, but they've got an incorrect derivative here. Now that's wrong. But again, I have to read with them, and their a prime of 2 is correct. So this is also a 101. These are some common student responses that we saw last summer. And briefly, here are some of the other common student responses, some other errors. If a student imported an incorrect h prime of 2 from part A, they were still eligible for all 3 points in part B. That might take a little time to read, but we felt that that was the fair thing to do. So, for example, if they used h prime of 2 equal 4, the y-intercept, we did enough of these to know that a prime of 2 is equal to 240. So once you read a couple of these, we know what to expect and what to look for. And unfortunately, there were some arithmetic errors here in evaluating a prime of 2. All right, so let's see if you've got the concepts down here. I'm going to try, Michael, if you're still with me, I'm going to try one of these polling questions. Our first one is a true-false question, which has to do, believe it or not, with the product rule. So I want to know if this is true or false. If I have the product of 4 functions, f, g, h, and k, and I want that derivative, is it equal to that expression on the right-hand side? So I think we decided we'll give you 22 seconds to answer that one. And
Be sure to answer. Sorry, Steve. Go ahead.
No, please go ahead. They should be able to answer. Go ahead, Mike.
Oh, sorry. I was going to mention that you can answer that poll in the lower right side of your screen.
So they should be able to answer that in 20 or so seconds, and then we should be able to tabulate the responses. Is that correct?
That's the plan. We'll see if it works.
Okay, here we go. All right, so let's see if they can sort of extend that product rule to a product of 4 function. Can you do it this way, or is there actually a different expression for the derivative of the product of those 4 functions? All right, let's see what we've got, Michael.
Looks like we had a lot of no answers.
How do you like that? Come on, we got to get some interaction here. Well, yep, this one is true. You can indeed do that. So that is an extension of the product rule. So, all right, let's try a second one here and see. This one's a multiple choice question. So can you see, Vickie, can you see my screen there? Can you see all 4 answers? possible
I
answers?
can. I see
All
all
right.
4 choices.
Beautiful. All right, Michael, if you can put that one up there. How do you take the derivative of f times g squared? So on the poll, you'll just see a dot next to those choices. So you have to look at my answers, A, B, C, and D, and respond there. Remember that this is anonymous. So we're not going to come back and say, oh, you missed that one. We'd like to know if you know how to do this one. Can you take the derivative of f times g squared? And we'll give you 20 seconds for that one.
And you do have to hit the submit button.
Well, maybe that's why we didn't have so many, well, we had so many no answers. Very good.
About 5 seconds.
Okay. Have to work under the pressure of an AP Calculus exam. How do you like that? Well, we got a few more responses there. All right, let's see. C is the correct answer. That's good. We still have those same 3 people guessing D all the time. All right. Well, that's good. Okay, yep, you do have to take the derivative of this. Take the derivative of f prime g squared, then the derivative of g. You have to use the chain rule. So, yep, the answer is C. Very good. Okay, I'm going to minimize that. I'm going to come back here, and let's pick up with part C, if that's okay. Mike, all right?
That works for me.
Okay, here we go, part C. So part C was worth 4 points, and as I said earlier, boy, there was an awful lot to do here for these 4 points. And the first point was for basically equating this limit expression up here to the number 4. Now, in student responses, this expression, this equating often appeared late in the student solution, and that's okay. It didn't have to be the first thing on the page. And in fact, in many student responses, it appeared after they applied L'Hopital's rule, and that's fine. It didn't have to be the first item presented. But somehow, in order to earn this point, the student had to connect this limit to 4 or show a correct evaluation of this limit. And I'm going to show you some examples in a minute or two. In finding this limit, the student did not need to mention that h of x is continuous. So let's take a look at a couple specific examples and see how the student could earn this point. So in example 1, here's a very simple way for a student to earn this point. They could recognize that h was continuous, and they could just start out by writing the limit as x goes to 2 of h of x is 4. They earn the point, and they could go on and try to earn the remaining 3 points here. In example 2, the student has conveyed the connection here, and they've demonstrated L'Hopital's rule. So actually, in this one line, if the student wrote that, they'd earn 2 points. They'd actually earn the first and the third point. In example 3, notice there's a subtle difference here. The student has made the connection for the first point, but that's it so far. There's no limit symbol here. So they haven't made or demonstrated L'Hopital's rule. In example 4, there's an error in the derivative in the denominator. I think there's a missing minus sign. So they have conveyed L'Hopital's rule, but not the first or the limit point yet. They could go on. It's possible they could get it, but they haven't got it here. In example 5, the limit point is not conveyed for sure. There's just not enough written here to convince me. And in example 6, even less information, they have not earned the first point. Okay, the second point in part C was for the value f of 2. Now, there were no bald answers accepted here. There had to be some supporting work. And often in presentations, we have a general philosophy given to us here. And the philosophy here in this problem is that we want to see the denominator set equal to 0. Now, the student doesn't need to mention L'Hopital's rule in order to earn this second point. And again, sounds kind of funny, but the answer has to be ours, f of 2 equal to 1. And again, down towards the bottom, here's some student responses, some examples, and focusing on the second point and how each was scored. Now, in example 1, the denominator of h is set equal to 0. we can see the correct value for f of 2, so this certainly earns the second point. In example 2, this is just another maybe different way to convey the denominator set equal to 0. We can see the correct value, so this also earns the second point. In example 3, that's not the denominator set equal to 0. So even though f of 2 is correct, this does not earn the point. Readers have to be careful in taking a look at student and reading student responses here. And in example 4, similarly, we have a wrong expression set equal to 0 with the right answer. This does not earn the second point. Okay, part C. The third point in part C was for sufficiently demonstrating the use of L'Hopital's rule. And let's just take a step back here and talk a little bit about notation. For the 2019 exam, if a student writes the limit is equal to 0 over 0, they did not earn the third point. Listen carefully. In 2019, for that exam, for that year, regardless of what follows. Now, that's not the same thing in my class. Many of us still use that notation as acceptable mathematical notation. We understand what that means. But last year, that was not accepted. However, if you take a look at these expressions at the bottom, student last year could have written an arrow to 0 over 0. They could have written 2 arrows. And they could have just written 0 over 0 with no equal sign. Now, you can probably tell I'm a little passionate about this issue. I think that this is valid mathematical notation. And can I just say that I'm in communication with the current chief reader about this issue. So there's no guarantee that this will change in 2020 or beyond. But I think that this notation is similar to writing something like a limit is equal to infinity. And if we're going to accept that as acceptable notation because we all understand as mathematicians what that means, I think we understand what this means. But it wasn't accepted last year. So here's the philosophy behind scoring this point. We need to see a limit of a quotient of derivatives. And that means we need to see a limit, we need to see a quotient, and then we need to be convinced that there was differentiation, attempting to see a differentiation attempted, and we need to see f prime of x in the denominator. And finally, the last point in part C was for the value f prime of 2. And there was an eligibility criteria here also. The student must have earned the third point, a lot to keep track of here. Unless the quotient was correct, but the limit notation was missing, or the notation used was incorrect. The answer must be our answer, and they cannot import an incorrect f of 2. Yikes. Again, lots to keep track of here. All right, well, here are even more examples as we put a lot of this together, focusing on the third and the fourth points. In example 1, let's see. I can see L'Hopital's rule here. I believe it's being used. So they get the third point, and they're eligible for the fourth. In example 2, I think I can see L'Hopital's rule being used here, a derivative of the top, a derivative of the bottom. Yes, there's an error in the denominator, but they earn the third point. They're not eligible for the fourth. Let's see. In example 3, I think I can see L'Hopital's rule in the denominator. So this earns the third point, but not the fourth. In example 4, there's no limit notation here. So this does not earn the third point, but this student is eligible for the fourth. In example 5, there's no limit notation. The derivative in the denominator is incorrect. So this does not earn the third or the fourth point. And finally, down here in example 6, the student has used, okay, quote unquote, bad notation. So they don't earn the 3rd point, but they could go on to earn the 4th. So a lot going on in there for 4 points, a lot of little things to keep track of as a reader. Michael, I'm going to try a couple of polling questions again. Here we go. Here comes another true or false question. So you probably all taught L'Hopital's rule already. So here's the question. L'Hopital's rule can be applied to evaluate any limit of the form. The limit as x goes to a of f of x over g of x. It's a really cool rule. And students want to use this all the time. So the question is, can you use it for any limit of a quotient like that? And we'll give you 20 seconds to answer that poll. And hope we get at least some more responses here.
And Steve, I know that while you were presenting, a bunch of people got back to me that, especially if you're on a mobile device, the poll pops up in front of the question, and so it makes it really tough to answer the question. So
Okay.
that may be some of that percent there. And I know there were some other people that the poll just wasn't working for altogether. So
Okay.
we'll see what we get here.
Okay. Hey, we got a few more answers there. Very good. That is indeed false. That is correct. You cannot apply that to just any old limit of a quotient like that. You must have an indeterminate form. Very good. Good job out there. All right, and here's one more multiple choice question. You may need a piece of paper and a pencil for this one, but this one clearly involves L'Hopital's rule. Let's see if we can find the limit as x goes to 1. This is kind of a cool question, I think. It's e times x minus e to the x over x squared minus 1. I'll give you a hint. You can indeed apply L'Hopital's rule to this one. So let's see if we can get an answer here. There are 4 possible choices in the spirit of AP multiple choice questions. And let's see if we get some answers to this one. Pretty cool. Neat that we can do this. Neat that we can see the mathematical expression on the screen too, even on a mobile device. That's pretty cool. Technology's come a long way. All right, what do you think, Michael? We getting any responses there?
Yep. Well, give me another few seconds here. Let me shut it down. All right.
All right, what do we got?
Give me about 12 seconds, Steve.
Okay. To collect all those answers? Okay. Pretty cool. Well, they're coming from a long distance. That's what it is, Michael.
Totally.
Hey, there we go. Indeed,
Yay.
The answer here is D. Very good. Excellent work. Okay. I've got one more question for you, but let me come back here. Let me go back over to part D. So very quickly, part D was worth 1 point for concluding that the function k is continuous at x equal 2 and for presenting sufficient justification for the conclusion. And here's some alternative or some alternate names for the squeeze theorem that were accepted. So the sandwich theorem, the pinching theorem, the squeeze play theorem, and I don't know who the heck is teaching something called the fly swatter theorem, but we accepted it anyway. And here are some names that we didn't accept in part B. Of course, the IVT, the MVT, the extreme value theorem, and Rolle's theorem. So here's a list of items that we need to see here in order for the student to earn this 1 lousy point. First, the student must answer yes, k is continuous. For justification, they must say that both g and h are continuous. Yikes. They must conclude that both of these limits are 4. They must therefore conclude that the limit as x goes to 2 of k of x is 4. And finally, they must conclude that k of 2 is 4 because g of 2 and h of 2 are also 4. So wow, there was a lot that the student needed to present in order to earn that 1 point. You can imagine there was a lot for readers to read in order to award that 1 point for students. All right, very good. I'm going to pass it over to Vickie in 1 minute. I'm going to leave you with one more question. This is not a polling question, but this is an open question for you. This is sort of an extension here, problem extension. I'm going to show you one more before we quit for the night. But here's one for you to think about. I'll give you 20 seconds, 10 seconds to write this one down. I think this is kind of a nice one. If g of x is equal to the square root of x cubed plus x squared, and that's times the sine of pi over x, see if you can find appropriate functions f and h. And since this problem employed the squeeze theorem, see if you can use the squeeze theorem to find the limit as x goes to 0 of g of x. That's kind of a neat problem. X cubed plus x squared, the square root of that, times the sine of pi over x. All right, Vickie, I'm going to try to assign this over to you, see if this works.
Sounds good.
Here we go. Here we go. How about that?
All right. Okay, let's see if my screen has popped up. So this should be a view of the TI-84. Some of you may recognize this graph if you have used a tale of two lines with the TI-Nspire, but I want to start with the TI-84 tonight and just talk about a few things. So this is basically looking at a visual representation of L'Hopital's rule and having students understand the idea of even continuity and differentiability of two functions. But what we have here appear to be two lines. We have a blue line with a positive slope and a red line with a negative slope. And what if we wanted the ratio of the slope of the red line to the blue line? Hopefully you could see, and I'll take my cursor and kind of point to some things, some places where the line actually crosses grid marks that I have here. So I have a grid in the background. And I can show you how we did this in a few minutes. But you can see where my cursor is here that I can move down 1 and right 2 so that I would say that the slope of the red line is negative 1/2, whereas with the blue line I'm going up 1 and over 1, so that slope would be 1. And I believe you could say that the ratio of the slopes of these two lines is negative 1/2 over 1, which would be negative 1/2. Now, the cool thing about this is that I am going to zoom here. We're going to zoom out and see if these are actually lines. But one thing I do have to change very quickly on the TI-84 is the delta X that we actually have. So I'm going to go to my window, and you will see that I have a very small window here from 1.99 to 2.01. I have my X scale is 0.001, likewise with the Y scale, and that is what allows me to have that nice grid in the background with this. So I'm going to change my X scale to 1 and my Y scale to 1, and we're going to look at the graph now. So I kind of lose that grid background at this point. And I am going to zoom out, and the nice thing is that sort of my zeroing in to zoom out cursor is centered at the intersection point, which you can actually see on the lower part of the screen is 2, 0. So let's zoom out here. So it takes a few minutes for the TI-84 to redraw these graphs. They almost look linear, but maybe not quite. And we're starting to see a little more curvature here. And I think now you can kind of recognize that, oh, we had a sine function and a parabola that both shared that intersection point at 2, 0. And so the value at each of those functions at 2 was 0. So actually we had a situation of having a value of 0 over 0. So if we wanted to find the limit as x approaches 2, we'd have a L'Hopital situation. And so the actual limit is negative 1/2. So if we think about this, the parabola is continuous and differentiable at x equals 2, 0. The sine function is continuous and differentiable at x equals 2 and y equals 0. And so we have basically what I like to think about and talk to my students as a situation of the functions are locally linear. So when we were very zoomed in, they appeared linear. They appeared to be their tangent lines. So when we were looking at that zoomed-in picture, we were looking at the ratio of the slopes of the tangent lines, which would be the derivative of the numerator over the derivative of the denominator that we were actually taking the limit of. And I think that's really cool. If you want to see what the functions were, they're pretty simple. So we had sine of x minus 2, and then we had a shifted parabola, x minus 2 squared minus 0.5 times x minus 2. And if you want to see where I actually got that gridded background from, it's under format, which is second zoom. So I went here, and it's the third row down, and I had a grid line. And as I said, I had to be real careful about how I set up my x scale and y scale so that I could actually count the slopes on those linear equations. You could use any functions to do this, but those two were the ones that we have in A Tale of Two Lines, which is a TI-Nspire activity. So I'm going to jump over to the TI-Nspire, and this is what the activity looks like. It's called A Tale of Two Lines, and it basically explains that the graphs intersect on the x-axis at the same point. We don't actually tell them that it's at x equals 2. And so again, you can clearly count the slope of the green line here. So we have negative 1/2, and then we have positive 1. So the ratio would be negative 1/2 to positive 1. The nice feature of A Tale of Two Lines in this case is that your zooming is just this bar that we can drag, and we gradually see our sine function and our parabola. And so we can talk about the same thing. There is a nice guiding paper that you can use with this activity. One of the things that I did want to show you is I set this up as just an extra page. So this is actually the limit we were asking them to find. And if you notice, the limit of the numerator as x approaches 2 would be 0. The limit of the denominator as x approaches 2 would also be 0. If we took the derivative of the numerator, we would have 2 times x minus 2 minus 0.05, and if we took that limit, we would get negative 0.05, and the derivative of the denominator would be the cosine of x minus 2, and if we took the limit as x approaches 2 of cosine of x minus 2, we'd of course get the cosine of 0, which is 1, so we get that ratio that we actually had with the tangent lines of negative 1/2 over 1. And I just think this is really powerful. I think students need a nice visualization to understand why L'Hopital's works. Steve, do we have any questions or comments or anything that I need to address here?
I don't see anything on the chat. Maybe Michael does. I didn't see anything come in.
Okay.
Nope, we're good.
Do you have any? Okay. Steve? You got any comments about this? I know you've seen this activity before.
Yeah, I think it's very cool. I've been thinking about if I could show L'Hopital's rule in some other way that where the value of the function is not 0. So this tale of two lines is always revolves around, is always associated with two functions where the value of A is 0.
Okay.
And that's generally the part of the proof that's given in most calculus texts. So one of these days, you and I are going to come up with a visualization off the x-axis, okay?
All right.
All right.
I can't wait.
Okay.
All right. I think you have another extension problem that you want to show. I do want to mention one thing while I've still got the control of the screen. Most of you know that there are some resources with the TI website that are called TI-Nfocus. So I went over something that was connected to L'Hopital's rule, but if you go to the TI-Nfocus 2019 AB6 and we go to the resource library, see if it'll pop up real quick here. Steve is going to mention a few of the things that he has here, but if you look down here, I think you can recognize from the screenshot what Tom Dick did with both the TI-Nspire and the TI-84. He did a nice little TI videos on the squeeze theorem. So that's something else that you might want to look at to help you with this, the two topics that are, I think, kind of predominant in this question. All right, Steve. Now I'm going to send it to you.
Okay. All right, here we go. So, as Vickie was just saying, this is part of the extension video that goes with AB6 from 2019. And this example is in the spirit of this problem. It's a little bit different in that this has a function defined graphically. So very similar sorts of questions, but just a little bit of a different twist here. We have this function h of x, which is an exponential function. The function g is defined on this interval -4 to 8. It consists of a half circle, a line segment, and then a quarter circle. So you don't have to worry about copying any of this down because, again, this is in the extension video for AB6 2019 that Vickie was just showing you. Given this question or given this setup, I have 4 different questions here, very similar to what we just did with AB6. See if you can find h prime of 3, find an equation of the tangent line to h at x equals 3, and sketch a graph of h in the tangent line. Here's a new function a. This sounds familiar. Find a prime of x and a prime of 2. And here's a little bit more complicated function where you have to find this limit. Notice that both h and g are in here. And remember that g, I'm going to sneak back here real quickly if I can. Remember, g was given graphically, so I don't have an analytical expression for g. I suppose I could find one, but I should be able to use the graph to evaluate that limit. So there are a lot of good resources, I think, on the TI website, and this is an example of some extension problems that are AP Calculus type questions associated with the concepts that were in AB6 last year. All right, Michael, I'm going to turn it back over to you. There we go.
Thanks so much, Steve.
There we go.
All right. Thanks so much, Steve and Vickie, for everything you shared tonight. As we begin to wrap things up, if you have any last-minute questions for Vickie or Steve, please try to get those asked. I know they'll do their best to get those questions answered.
I see one there, Michael, about 0 over 0 again. Let me try to make that clear. Maybe, Vickie, you can help me a little bit. Last year, a student could not write that the limit of that quotient was equal to 0 over 0. They could put arrows. They could just put 0 over 0 without any sign in there, but they couldn't write equal 0 over 0. Now, I don't know if that's going to change at all in 2020 and beyond, but to be on the safe side, I would not write equal 0 over 0 on the exam in 2020.
Great tip. Thanks, Steve. Let me take a minute and share my screen. There's a couple of resources that I think we had a question about. And one of them was, again, where those extensions that Steve just did can be found on our website, education.ti.com. If you go into the Resources tab, you'll find the TI in Focus for AP Calculus. And again, that's where you can find those extensions that Steve was working through, along with a bunch of other really great resources to use in your classroom with your students. Under the Professional Development tab on our website, if you slide down to the middle, find Webinars, and then look at our on-demand T-Cube webinars. If you missed parts 1 and 2, feel free to select a topic and filter it down to exam preparation, and there you'll find our part 2 and then part 1 that we did in this series. Steve and Vickie, correct me if I'm wrong, but I believe part 2 focused on exam problem AB3, and part 1 was AB1, I believe.
AB4?
I think it was AB4.
Okay. AB4.
Thanks. You guys have a much better memory than me.
Sorry.
But we did those AP problems as well as, again, looked at some other extensions, I think, in each of those webinars.
We did indeed.
All right,
so
there
I
is
think,
one question.
Yeah, go ahead, Vickie.
Mike, No, it's just how will we know if that notation becomes acceptable? I think the best thing to say there is for students not to use that notation, and that's just the best direction to go right now.
Yep.
Even if it becomes acceptable, I don't know that it'll always be acceptable. So it's best to look at what the theorem actually says that allows you to apply L'Hopital's rule, and I just encourage my students to write the limit for the numerator, the limit from the denominator separately, and then say, oh, I get to use L'Hopital's rule. It's an indeterminate form. I mean, they don't write all that down, but that's basically how we discuss it in class.
Yeah, that's the best way to do it, Vicki. I mean, when I teach this in my class, of course, most of our students try direct substitution first. And
Yes.
if that gets you to 0 over 0, I always use that in my class as a signal that, you know what, you need to do something. Because I don't know what 0 over 0 is. That's a signal that I need to do something else mathematically. So I do use that notation in my class, but I think that's good advice. Don't use it on the AP exam for now.
Right.
Thanks so much. I know that many of us may be looking towards summer sometime soon, and for those of us that are, I know, you can learn about some summer workshops that are being hosted around the United States. Some focus on different pedagogy or technology. Feel free to visit our website to learn a little more about what workshops are coming where. Also, we said that for one lucky winner tonight, we're giving away a summer workshop registration, and tonight's lucky winner is Pam Benny. So, Pam, congratulations. We hope to see you at a T-Cube summer workshop along with everyone else tonight. Pam will also be emailing you in a couple of days to give you a little more information about that. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we help plan future online events, and we really hope you share your thoughts. Feel free to stay connected and continue some of the conversations that were started tonight on all the major social media outlets. To receive a certificate of attendance, go ahead and click that link that just appeared in the chat window. Also listed is a link for the documents that were used tonight by Steve and Vickie. If you're watching this on demand, go ahead and copy that link in your favorite browser to receive your certificate. Lastly, if you're in need of some post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or send us an email, ti-cares@ti.com. Thanks so much, Steve and Vickie, for everything you shared tonight. We hope everyone out there is safe and well. And we hope to see everyone back online next week. Have a great night. Thanks again, Steve and Vickie.
Okay. Thank you very much, Michael.